This week we've learned a lot about branching and jumping instructions and how we can use them to emulate features like if-else's, if statements alone, for loops, while loops, do loops, a lot of high level language features that we take for granted. Of course, when we're down at assembly language level, we have to do a lot more of the hard work ourselves. So what I'd like to show you today is how to write some code using branching and jumping instructions to sum an array. This is just a general example so that you can see how you would use branching and jumping to access elements of an array for whatever means you might wish. But so far I've set up an array called R. I've given it 5 values, all with the value 1, just so that we can test our answer at the end very easily. And I've used a value called last position, so I'm going to assume that I know the length of this array. Last position is at position 4, of course, because the first position is at position 0, so we're incrementing from 0 upwards. Now I'm going to use a for loop for this one, so for every element of the array, add it to the total. And to do that I need to initialize values first. So what I'm going to do first is I'm going to load the address in, and the address of the array and the size of last position. So I'm loading address, using this as a pointer. So there we go. I'm going to load the word into T1 of last position. And that's my initialization done. Now you might think I need to initialize an index, and you would be right. However, I know that the index is going to start from 0, so I'm just going to use an address, or a register, sorry, that's already set to 0 without, so that I don't need to write another line of code. You might notice in this code that I'm going to write, it's not the most efficient code in the world. It might be a useful exercise for you to see how efficient you can make it. I'm going to go through it in what I think is a fairly straightforward way so that we can all understand it more easily, and sacrificing some efficiency along the way. But let's go back to the code. So first things first, I need some labels. I need the start of the loop and the end of the loop. I need the start of the loop because I need somewhere that I can jump back up to once I've executed the code block. And then I need an end that I can jump past all of the code in that block to finish up. So I'm going to call this sum loop. And I'm going to call this one end. So there we go. I have the start of my loop and then I have the end of my loop. So far so good. Now the first thing I need to do is I need to check that I'm not past the last position. So what I'm going to do is I'm going to use branch greater than. I'm going to assume that my index is stored in T2. T2 is of course 0 at the moment, so in the first case we'll be testing as 0 greater than 4, and if I get these around the right way anyway, then that should be a no. And we'll continue to go through the code. So this should be T1, and I jump to end. So this is testing is I greater than 4. We're using greater than 4 because we want to check, we want to sum the position 4 itself. We want the last value to be included. We don't want to stop at position 3. So that's the first thing done. So if I pass this, then I need to think about what I should do next. The first thing I should do is I should increment my index to create an offset. So we know that we would use 0, 1, 2, 3, 4 for this array where we're in a high level language, but we know that since we're down here at a low level, we need to increment by multiples of 4 because we're storing words. So instead of 1, 2, 3, 4, I need to do 4, 8, 12, 16. But I'm going to automate this using shift left. And I'm going to store the value in T3, and we're going to shift the value in T2 by 2. So I'm using T3 because I don't want to change the actual value of the index. I want to increment that every time we go through the loop, but I want to shift it and store it in a different place because I don't want to overwrite the actual index itself. I don't want to do that because if I incremented if I multiplied the index and then add 1 to it after like one and a couple of loops, I'd be way past the end of the array already, so that wouldn't work. So here, this is the equivalent of timesing by 4. Remember that 1 position is a multiple of 2, 2 positions is 4, 3 positions is 8. So we go up in powers of 2. Okay, so now that I have that, what I want to do is I want to add that value to the pointer stored in T0. Remember, T0 is storing the memory address. So if I just add the offset to that value, then I will get the position of the next element in the array. So I want to do add, and I can store this in T3. I could overwrite this value, and I'm going to add to the value in T0 the value in T3. I'm overwriting it just because when I do this, I don't need to use it again until I'm in the next loop, in which case the shift left instruction will overwrite it. So this is the next address. Well, if I could spell address, we would be in a good place. In memory. Okay, so now I have the value of the next memory address, so I want to load the word at that address. So I'm going to load the words into A1. Now remember it's a pointer, so I need to use the funny notation of T3 like that. So that's saying A0 is equal to R at position I. This is what would be in the high level language. Of course down here we're in the murkier level. And I'm going to add that value to what's in A0. Because A0 is going to be my running total, so this is going to be the same as saying that the total is equal to total plus A1. Or actually, what would be a better thing to say as array at position I. And up there that should be A1, not A0. So there we go. So that's me added the value on. Now I need to increment my index. What I'm going to do is I'm going to add to T2 value that's in T2 with 1. So this is my I++. So now I've incremented, and now I should be able to jump to the top of my loop. So I can jump to some loop, and that should be me done. Now what I'm going to do at the end here is I'm going to load the immediate value into V0 of 34, so I print out the hexadecimal value and do a syscall. Now hopefully, if I've done this right and I've gotten these bits up here around the right way, I should be able to sum this up and I should get the value of 5 out because they all contain the value of 1. So let's assemble this, hope it works. So it assembles, run it, and we get 5 out. So there you go. That is how you would sum an array in MIPS. So we could change these values, we could chuck an A in there, we could chuck, let's say, a C there. Oh, why not, let's throw a F in there, and an A at the front, and we could assemble this again, run it, and we'll get a much bigger answer out. So you can get, so this is generalized for any array of this size now. So it's quite powerful being able to use branching and jumping instructions in MIPS. Now, as I say, I think you could probably make this code more efficient if you wanted to, using less registers. Maybe using less instructions, I'm not 100% sure on that. There's probably a way to do it, but I'm not 100% sure off the top of my head. But either way, this is how you would sum a basic loop or basic array using MIPS. I hope you found this useful, but if you have any questions about anything we've covered here, please do let me know. Thanks.